Okay, Luke, so we're back, and I think it's time to talk a bit of, say, fundamental physics, the things that we have to deal with when we want to learn something about the universe. And so this is essentially related possibly to a viewer's question. But, when you get to university, you start talking about various things, and then there's this concept of a field. What is a field?
What is a field? Well, so let's just roll back in time. So when you turn up at physics, the first thing they start, teaching you is Newton's ideas about the universe. And for Newton, it's just all particles. And so his is a theory about how particles move around under forces from other particles. And even gravity, there's no real sort of field there. That's not an idea that's there for him. It's a spooky action at a distance, but it works. So that'll work.
So for Newton, you have two masses.
Yep.
And you ask, how does one mass influence the other mass? And you talk about the force between them. So this mass produces a force on that mass. This mass produces a force on that mass. And then things do their things according to his equations of motion. So you can use F equals ma. You can calculate what happens to the masses.
Yeah.
So there's nothing wrong with that picture. It works, right? So what happens next?
It's fine, but what happens next is we start to discover things. Well, physicists start to discover things like electricity and magnetism. And in putting together the rules that those phenomena obey, Michael Faraday in the 1800s works out that it would be helpful if we thought of the influence of electricity and magnetism as something sort of spread out through space and time.
Okay, but when we teach electromagnetism, we start with something like Coulomb's law. And Coulomb's law says if you have a pair of charges, similar to the way that Newton said if you have a pair of masses, you can calculate the force of one charge on the other charge and vice versa.
Yep.
And then you can use F equals ma, Newton's laws of motion, to calculate what happens to the charges. And you actually have a similar thing for magnetism, right? So magnetism you get created by a current.
Yep.
So if you have a chunk of current and a charge, then there is a relationship between the current and the charge that tells you the force on the charge, and then you can calculate how the force behaves, how the charge behaves because of that force.
So there's a difference between electromagnetism, electricity, magnetism, and gravity. When you do this thing for gravity, the force on this particle over here with mass depends on where this particle with mass is right now. And so to keep track of everything, you just need to know where everything is now and how it's moving. With, say, electricity and magnetism, if I've got a charge here and I've got another charge here and I move this charge, this one doesn't move straight away. It reacts a bit later. So the way that we sort of fill that out is it's reacting to where the other charge was a certain time ago. And so in some sense that we're going to have to put together somehow, the information about I moved over here takes some time to get over to this other charge. Now, do we want to talk about information? How do we want to flesh all of that out? What Faraday thought was, okay, let's imagine there's a field here, and when I move this charge, it changes the field, and the field sort of ripples a bit, and those ripples take some time to get over to the other charge, and this charge here responds not directly to this charge, the second charge. What it's responding to is the field that was created by this charge, and which takes a bit of time to react when you move it around.
Hang on.
And so there's a sense in which we're just sort of, we're trying to take account of the fact that these things I don't just have to keep track of where everything is now. I have to keep track of where it kind of was a while ago. And that seems what the field is doing.
But when we say a field, what do we actually mean? Right? I mean, but not the philosophical, right? So what we're really saying is that we have a charge. It creates something we call an electric field, and that electric field is everywhere.
Yeah.
So
that's the key.
Fills all of space, and it has a particular value at every single point. And because the electric field is a particular kind of field known as a vector field, not only does it have a value at every point, it has a direction.
Yeah.
Okay? So we say that this charge fills the entire universe with a field that has a value and a direction at every point, as does every other charge.
Yeah.
And as you move these charges around, that changes these fields. And as you mentioned, there's a time delay in how the fields respond. There's a ripple that travels out. And as you move charges around in that field, that also produces another field called the magnetic field, right? So we get that each individual charge produces this thing that fills all of space, and other charges are reacting to the field in their vicinity.
So maybe a good way to think about it is just mathematically. When I boil it down to what do I need to do mathematically, in Newton's universe, what you need is the positions of all of your particles and their masses and their velocities. Okay, so what you end up with a mathematical object, which is for each particle in the universe, I just have a list of all the particles. Okay, and for each one, I just have where it is, how fast it's going, and how much it weighs, its mass. When you get to this field idea, you need a different kind of mathematical object. You don't need, okay, where is particle 1 and I get X, Y, and Z. You need something where I put in a location in the universe and a time, an X, Y, and Z, and a T. I've got to put that into a mathematical function, and out the other side has got to come the value of the field. Now, depending on how many numbers come out, depends what type of field it is. You're talking about a vector field, so 3 numbers come out, a direction and a length. And so mathematically, that's a sort of a big change. The fundamental thing, mathematical thing we use to describe the universe changed from Newton to Faraday to these fields. And so the question now is, okay, we've done all of this. We've got all this apparatus that you said. Is it just a calculating apparatus, or is this really part of, the furniture of the universe? And I think the reason why we treat them as real, for most physicists, maybe if you get them down at the pub later on, they'll have some different thoughts. But for most of the time, we treat them as if they're real. If you don't treat them as real, you have a few problems with the conservation of energy. So I take a particle over here. Okay, here's my 2 charged particles, and I wiggle this one. Okay, so I've put some energy in. Okay, and when I look back later, that the particle has slowed down, so that the energy of the wiggle has gone, and so this particle's still, and that particle's still, and then sometimes later, this particle starts to wiggle over here. Okay, now if you're thinking about conservation of energy, that's a bit of a problem, right? Because you put some energy into the system, and then it went back to where it was. And then some energy turned up over here. Whereas if you think the field is real, you've got a great explanation for that. I wiggled the particle, energy in the particle wiggled the field, the energy's in the field, and it's traveling, and then it turns into the energy of this particle wiggling. And so now we've got a nice picture where there's always, the energy's always there, I can always account for it, and it's always in some real thing, rather than having to say something really weird like the energy was in the particle and then it was in my calculations, it was in my convenient, accountants, it was in my spreadsheet for a little bit, and then it went back into the universe and made something else wiggle.
Okay, well, I'm gonna be a bit hopstropolous then, because I'm one of those ones that I'm not a big fan of saying that fields are real.
Okay.
In the sense that, yes, it makes you feel comfortable because you can talk about the conservation of energy, but for many people, conservation of energy is a comfort blanket more than anything else, right? It's an accounting tool.
Right. Okay.
And in fact, when we look at various aspects of physics, you invent things to ensure you can do this accounting tool. So you can talk about energy going from one place to another place, and it's always in something, but energy is one of those slippy sort of concepts in that you can't really put your finger on what it is, but you're happy that it's conserved. And as we've spoken about previously, it's not conserved necessarily.
That's one of the, I'll put the link up there. Energy is not conserved in cosmology, which is a real
But why does it bother you? It only bothers you because when you were in high school, it was drummed into you that energy is always conserved, right? But,
well, here's why it bothers me. So, I mean, there have been various attempts over the sort of history of physics to say, what physics is really about is just predicting stuff. We're not really interested in what the real furniture of the world is. And I have a problem with that for two reasons. One, I don't think anyone really does that. No physicist actually thinks that all they're doing is just predicting stuff. I mean, the whole point of physics is to try and say what's out there. And the second, there's this sort of famous phrase by a philosopher of physics, Hilary Putnam, who said, it would make it's called the no miracles argument. If physical theories aren't really about something out in the world, then their success would be a miracle. Like, I mean, why on earth would any of these theories work if they're not actually describing something that's out there? And so, if you want to interpret electromagnetism in a way where the fields aren't real, I still want an account of what stuff is out there and why does this theory work? If it's not working, if it's not part of the real furniture of the world. So the reason why the lack of conservation of energy in cosmology really bothers me is that the conservation of energy seems to let us say, okay, whatever this energy thing is, it's part of the real furniture of the world. And the fact that it's not conserved in cosmology is a real bother then, because apparently the universe as a whole doesn't care about this energy stuff. It's happy to let some of it slip away somehow. So I'm sort of torn between these two things. You don't want to do the word is reification. You don't want to take your theories too seriously and say that everything that physicists talk about is really real and really out there. But there has to be something we're doing which connects with the real world. Otherwise, it's kind of miraculous that you can take our ideas and then design computers and software and microphones and all that sort of stuff.
My counter.
Yeah,
okay. So. Richard Feynman, right? Great physicist of the 20th century. One of the problems that he wanted to calculate was related to this concept of the electric field. And the question was, if we take an electron, okay, what we say is that electron is positively charged, so it's surrounded by an electric field. So there's an electric field around that electron. And Feynman asked himself a couple of questions, and I won't do the exact question, but along the way. So if you took a universe and you put one electron in there, how would you know that there's an electric field around that electron? The electric field doesn't mean anything until there's another charge involved, right? So the other thing that Feynman wanted to do was to calculate the energy stored in the electric field. Okay, because there's a potential there. You put another charge there, you can get a force acting on it. It can accelerate due to the electric field. So there's energy right. in the field. So you want to calculate that for something like an electron. So you can integrate over the electric field to calculate the energy. And the big problem you run into is that when you ask yourself how big is an electron, well, the electron has no physical size, and so you basically have to keep integrating that field down and down and down, and the field gets stronger and stronger and stronger until you get this answer that the electric field, due to the electron, has an infinity in it.
Yeah.
So Feynman struggled with this, right? So he said to himself, well, what do I do? How do I fix this problem? And essentially, in a very roundabout way, what he did is he banished the concept of the electric field. Okay,
right.
So Feynman went back to this picture that charges talk to charges directly. You don't need to put a field in the way of the classical electric field. You still have your quantum fields.
Yeah.
Okay, but when you have two charges, they talk to each other by a ripple in the quantum field, which is the photon which is exchanged between them.
Right.
But if I take this other charge away and this electron's got nobody to talk to, then that quantum field is zero. There is no electric field around the electron.
Okay.
So the classical electric field is an approximation of when you have lots of these quantum things going on, and that produces your classical field.
Right.
But if you take an electron and put it on its own in a universe, there's no electric field around it. So you don't have to worry about those divergences anymore. They go away because you banish the concept of the classical electric field. So that then begs the question, was it ever real to start with?
Okay, so let me just take us on a bit of a detour. So there's an idea, people try and work out what does it mean to be a physical theory or a physical law. And it seems like there's a difference. You might say something like, well, it's some statement about our universe that holds universally. And then other people said, well, actually, that's not quite enough. You could have universally true statements that we don't think are laws. So suppose it's true that everyone who is exactly 1.80536, just give a lot of decimal places there. Everyone who is exactly that tall on this day is bald. Suppose that statement is true. Suppose it's then a universally true statement. It's true everywhere. But we wouldn't call that a law. It's just a generalization. And in trying to nail down, okay, why exactly isn't that a law? There's a concept which I actually find quite interesting and possibly quite useful, is the idea that a law is supposed to, and there's a technical jargon here, it's supposed to support its counterfactuals. And what that means is, okay, suppose it was true that everyone who's exactly that tall is bald. It's not true that if someone became that tall, they would instantly lose all of their hair. That we don't think that's true. So the counterfactual, which is the sort of what if scenario of, if I suddenly became that tall, would I suddenly become bald? Well, no, we don't think that's true. And so the statement everyone that tall is bald is not something that's is just an accidental generalization. It's kind of always true. Whereas for a law of nature, we think that something like that is true. If I say, here's two masses this far apart, what is the force between them? We think that law is universal because it could be true even if no two particles were ever that mass and were ever that far apart. So we think that we not only can use these laws to talk about our universe, but to talk about other ways the universe could have been. So thinking again about that electron in empty space with just the electric field around it, doesn't really have an electric field. Well, it seems to me if you've got a law, you should be able to say something like, okay, it does because if there was a second particle, it would behave as if there was a field there. And it's that sort of, having the ability to describe scenarios that may not actually happen, which makes something a law. So now getting back to the field idea, I think the Feynman example is good. We've sort of gone off the deep end here, haven't we? This is great. The Feynman example is great. I think what it shows is that actually, maybe in the theories we have, if we're going to say a field is real, we'd better be able to. It better be all self-consistent and nice. There better not be. So what Feynman, I think, what he's discovered there is that actually in the idea of a classical field, there was this lurking infinity. So we shouldn't have promoted that thing to sort of being real without some, at least some fixing up, some sticky tape or whatever, just to get that infinity out of there. But again, I mean, there's a difference between saying the field isn't real to saying I've got a better description of what's really going on here. Because he still wants to say, I assume, that photons, in some sense, are part of the furniture, right? So, what is a field? We went off the deep end there, as we always do. For me, it's, the classical idea of a field. I think our best description of the world, where on the classical level, where we don't end up with, sort of a miraculous, I have this sort of calculating device, and then hey presto, the universe actually works, something like that. What best accounts for that? Fields are part of that best account of the furniture of the world. But I don't think that ever gives us the right to say, that's definitely a real thing, and that no future theory could possibly revise that list of furniture.
Yeah. I think it might be one of those lessons from physics, right? Is that I think anytime somebody says that this is the way it is, it's guaranteed that the next theory that comes along will say, no, it's not.
And it still bothers me that energy isn't one of those things, but I'll just have to deal with it.